I have them numbered according to our review packet, but in any case, they're just examples if the numbering doesn't mean anything to you. So we will start here. We're given a function from A to A in terms of its ordered pairs. So this is kind of the relation notation for a function, and then we want to answer some questions. The first thing we want to do is find f compose f, okay? And I will do this in this relation notation as well because f was given to me this way. So how do we do this? Well, if you go back to functions, f, okay, the first coordinates in each ordered pair are the elements in the domain, and then the second coordinates in each ordered pair are the elements thinking about them in the codomain or the image it would be, and then this maps to this. So f of 1 is 5, f of 2 is 3, f of 3 is 4, f of 4 is 1, and f of 5 is 4, like this. So when we compose, okay, well, f of 1 is 5, and then that would be this first one. Then you evaluate f of 5, okay? So we want f compose f of 1. 1 maps to 5, 5 maps to 4. This would be 4, okay? And then f compose f, let's see, of 2, because by definition, the composition, in fact, we can answer this one right here. This is by definition. There's nothing special about this f. That whenever you have a composition, the domain of the composition is always the domain of whatever happens first, which is, in this case, they're the same, but it's whatever happens first. And so we will have a ordered pair in my function, f compose f, for each ordered pair in f, because we have the same domain. The domain will be 1, 2, 3, 4, and 5, like this. Okay, so 2 goes to 3, 3 goes to 4, and then I need to figure out where 3 goes, where 4 goes, and where 5 goes, and then I have f compose f. Where 4 goes and where 5 goes. Okay? Well, 3 goes to 4, that would be the first one, and then 4 goes to 1, so 3 goes to 1, and then we're almost done with this part. 4 goes to 1, 1 goes to 5, so 4 goes to 5, and finally 5 maps to 4, and let's see, 4 maps to 1. So f compose f of 5 is 1. Okay, so this was f compose f. Now, this we already answered, and this was true no matter what if we could even have f and g, and we could have g compose f or f compose g, the domain of that will always be the domain of whatever happens first, as I said. Now let's do the second one. This is not always true, so we really have to think about this specific one. Well, let's see. In fact, I'll write it even here. What is the image of f compose f? I'll write it here because I have space here, but it's really to think about this. Maybe I'll put this in a red box. Well, this is the set of all second coordinates of elements in f compose f. So we have 4, we have 1, and we have 5. 4, 1, 5. That's it. Okay? On the other hand, if we want the image of f, well, we look in f and we look at the set of all second coordinates of elements in f. This is 5, 3, 4, and 1. 5, 3, 4, and 1. Okay, so we see the answer here. These two are not equal. The answer is false. And the reason is, let's see, 3 is in the image of f, but 3 is not in the image of f compose f. And so the two sets are not equal. We also see them here. Okay, next we look at the relation defined on -2, -1, 0, 1, and 2, where A relates to B if and only if the product AB is negative. we would like to list the elements of R and prove R is not transitive. Well, okay, this is ordered pairs. So I need the product to be negative. What does minus 2 relate to? Well, it relates to 1, it relates to 2, and then, of course, I could have the flip of these because like this and like this. We will see, in fact, you can see almost by looking at the definition that this would be a symmetric relation because if you interchange A and B, it's the exact same statement. Okay, so when I put 2 in, I will put the flip, that's what I call it, of them, where I interchange the X and the Y. Okay, so here are 4 elements, and that's everything. I have everything that minus 2 will appear in an ordered pair. And now let's do minus 1. So we have minus 1 will also go with, or relate to, I should say, 2 and 1, like this. So I have minus 1, minus. Okay, good. And now anything else? 0 does not relate to anything, because the product of 0 and some other number is 0. And then you don't have any of the 2 negatives related to each other. You don't have any of the 2 positives related. So you could even go back to our counting days, which we do now sum 2, but you can realize you have everything because you would just choose 1 negative number, there's 2 choices. 1 positive number, there's 2 choices. That would give you 4, but then you have to choose an ordering of which one comes first, and that's another 2. So we have 8 elements in this relation, as we should have. Okay, this is everything. Now let's prove R is not transitive. Well, we can do that just by looking at the ordered pairs. So to not be transitive, what we need is, it's an example, right, of let's say A comma B in the relation, a B comma C in the relation, such that A comma C not in the relation, like this. So we can just glance and make many examples, but right here, let's do the one that I saw first was this and this. So we'll just say, notice that 2 comma 1 and 1 comma minus 1 are both in R, okay? However, so this is one of these examples, the middle ones match. That's the way I always say with transitive. However, minus 2, minus 1 is not in R as, well, multiply, which is strictly bigger than, well, I can say bigger than or equal to, it's fine. That would be the negation of this, okay? So this is an example which disproves being transitive. It's not the end. There was one more part, which is C. We need to decide true or false. That's a good thing I checked the problems I'm doing. R equals R inverse. Well, I actually already discussed this, right? One thing that we proved, in fact, part of it, one direction, is one of the problems I was going to go over, but it's something from class that R, or maybe it was from homework, for example, that R equals R inverse, the inverse relation, if and only if R is symmetric, and this is without a doubt symmetric. The answer here is true. You could also, if you wanted to, take every single ordered pair and interchange X and Y, and you will, that would be R inverse, right? And you will realize you had the exact same relation. So this is another option. But this relation, by its sort of fundamental in its definition, we see that it's symmetric, and that allows us to answer this question. Okay, now I'm actually done with the problem, so we will move on. Okay, next one. How many people are needed to guarantee at least 5 share the same birthday, but perhaps in different years? Now, I do mention in this problem that you have 366 days possible. So there's no confusion as to whether or not to count February 29th. We certainly had one this year. Well, okay. So we have 366 possible days someone can be born on, right? Okay, so how many people are needed to guarantee? This is generalized pigeonhole principle. And so let me just write a little bit about it. If capital N is our number of people, and then we would have, this would be our pigeons. And then if we have 366 days, this would be our pigeonholes. What we want here is, we want to find capital N. So we want, and we want this, we want the smallest one. How many are needed? This would be the smallest capital N, such that you can guarantee at least 5 share the same birthday. So this would be capital N such that, well, if you think about the generalized pigeonhole principle, we would need this. The ceiling of N over 366 equals 5. Okay? This is what the generalized pigeonhole principle says. And in fact, we did that in a video. Okay? It was not in class, but it was in a video, which is what we have this semester, at least this part of the semester. Okay, well, all you need to do is just, so we can solve for N. You can just take N to be 366 times 4 plus 1, and this will be, now I need to look because this is the arithmetic I don't do in my head. I have 1465 as our capital N. And you could check that, for example. You could check it with your calculator. Take 1465 over 366, and you will get 4 point something small. If you take the ceiling, it would be 5. Okay. This is about the equivalence relation, which is congruence modulo 6. And I rephrased part B from the way it is in the worksheet, but it's equivalent to what I have written. I just wrote it in a different way that we can work with that matches a little bit more. But in any case, we want to find x and z with the class of 5x equals the class of 1, and then prove by contradiction there is no x and z with the class of 2x equal the class of 1. Well, I like this exercise because it really makes us think about equivalence classes and think about the notion of the mod n relation. So we know here, this is just, we just need to find the x, but I'm justifying. So we know the class of 5x equals the class of 1 if and only if, well, we know from equivalence classes that the classes are either equal or they're disjoint, and they're equal provided the representatives are related. Okay, we proved this in class. So 5x is congruent to 1 mod 6, and this is, let's say, if and only if 6 divides 5x minus 1. Now at this point you can just start thinking. So let's see, is it 2? No, 5 times 2 is 10, minus 1, 6 doesn't divide 9. Is it 3? 15 minus 1? Nope, right? You just start playing to find an x. 4 would be 20 minus 19, 6 does not divide that. But 5, here we go. So you notice, so we will let x equal 5. Okay. So this is my answer, but now let's see why this is my answer. Then 5x minus 1 is 5 times 5 minus 1 is 24, and 6 divides 24. So this one works, right? This is what we needed. So this 5 works is an x such that the class of 5x is the class of 1. And then this is what I changed from the writing here to here. I said that this behaves like a fifth. It's called a multiplicative inverse, mod 6. And then this was in that language, but it's equivalent to what I have written here. So in any case, we have found the x. That works here. And now let's work with the second one. Well, to prove by contradiction, this is a non-existence, right? So we would assume there is. So by contradiction, we assume we have some x. There exists an x in Z with, and I am still working mod 6 here. So the class of 2x equals the class of 1. Okay? Then, what does this mean? So then we just unravel, sort of as we did in the first one. So then 2x is congruent to 1 mod 6. And then, well, this would mean that 6 divides, comma, maybe meaning that 6 divides 2x minus 1. Okay, so thus, there exists an integer, maybe y in Z, where 6y is 2x minus 1 with, this is just definition divides. And now we are almost to our contradiction. We can, let's see, let's solve for 1 here. I can move the 1 to this side, move the 6y to the other, and I get that. So rewriting, we have that 1 equals, what did I say? Move out to this side, we're going to get a 2x minus 6y. And now we factor out a 2. Okay, we are almost at our contradiction, because look, what does this say? So as x minus 3y is an integer, we see that 1 is even. And this is definitely not the case. 1 is even, which is a contradiction. Is a contradiction, because 1 contra is odd. Okay, I had just enough space for that one. And so we have proved, in fact, that there is no x where the class of 2x is the class of 1. We practiced in our review session yesterday proving, we had an example proving something's 1 to 1. We had an example proving something was onto. And you could prove this is a bijection by directly showing f is 1 to 1, f is onto. Okay, now there's another way that I want to do, just to, because we can, and we've practiced certainly, and I'll do another one today where we prove things are 1 to 1 or onto. But one thing that you can do specifically for a bijection, okay, so let me put this in stars. One approach is we can find a function g that maps from R to R and show that G compose F is the identity on R. This is with F going first, and that F compose G is the identity on R. This is with G going first. And then we conclude F is a bijection. In fact, we know more than that. This was something that came up in, I don't remember which functions video it was, but one of them. One way you can prove something is a bijection is by finding a function that goes the other way And in this case, the domain and codomain are the same, but I'm starting from this R and going to this R, such that when you compose in each direction, F compose G, G compose F, then F is invertible and G is F inverse. Okay, that was a theorem we proved. But I'm not trying to find the inverse per se. All I'm trying to do is show F is a bijection, but I can use this. And one thing that I will do, one more step before I get into my proof, is I'll make a little, I'm trying to figure out what color. I will make a little side work box over here. Maybe I'll do it in black. Okay, so this is side work because I have to figure out what G is going to be. And this might take you back to some math class in your past where you found inverses of functions, just calculate them, right? So if we have y is 3x plus 1, what I'm trying to do is find g that goes in the other direction to prove f is a bijection. Well, I would just solve for x. So I have 3x would be, let's see, y minus 1, and then x is y minus 1 over 3, like this. And then I don't even need this part. Okay, so this is a side work box. That's part of my calculation. Now I will, maybe let me box all of this off. This was just what I'm going to use is this part. And now I'm ready to get to my proof. Okay, all of this here, I could have just put on scrap paper, something like this. But now let's get to our proof. Okay, proof. Well, let's define G from R to R via, now I'm going to use y here, G of y, just so that I try and keep my x's, maybe I'll write it here. The way I'm going to write it is my x's live here, and then think about y's here, and so y is f of x, right? And then when I go the other way, y's here and x is here, x is like G of y like this. Don't have to do it this way, it's just the way that my mind is organizing this. So G of y is here, although I need to make sure this whole thing is divided by 3. G of y is y minus 1 over 3. We could have used the same letter, x, in this case too, it's fine. So then, period, to show or to prove f is a bijection, it suffices to show, and this is because of a proposition we proved, as I mentioned, it suffices to show, oh, now I can write way over here, that f compose G is the identity on R and G compose F. Okay? So I mentioned that, this was not part of my proof, I mentioned it now as my proof, and so I'm making the comment that this is all I need to do to prove F is a bijection. Okay, well, this is just a calculation, really. So we let x in R, okay, then, and so I'm going to do this one because I'm feeding x's into F, I'm feeding y's into G, although, like I said, the letter choice was just a personal choice I made, but I have G compose F of x equals, well, it's G of, and now I put in F of x, 3x plus 1, and now G, well, we stick this entire thing in for y. So I have 3x plus 1 minus 1 over 3, 3x over 3, which is x. And now I need to do, right, so I have shown that G compose F is the identity. Now I do the other one. So then we let y in R, then now I need to compose the other direction. Okay? So then, oh, this tilts down, but I think we can read it. F compose G of y. This is F of y minus 1 over 3. Now I put this into f. So this is 3 times y minus 1 over 3 plus 1. And this is going to work out nicely. This gives me y minus 1 plus 1 equals y. Okay? So we have shown that f composed g is the identity on R. And so we have shown, so thus, f composed g is the identity on R, and g composed f is the identity on R, and this is what we needed. Okay, so I could put another line like therefore f is a bijection, but number 1, I'm out of space. And number 2, I've already mentioned that this is what I needed to show in order to prove f was a bijection. Okay, so this is a little bit different of a way, and I think I remember doing an example like this in our functions video, but I wanted to do another one just because it's a really nice application of that theorem. Now my numbering has changed. This is now number 1. I sent out a second sheet, which was just some more problems that I pulled off old exams. And so this is number 1 off that sheet. Okay, well here z sub greater than or equal to 0 is non-negative integers. So 0 plus the natural numbers, 0, 1, 2, 3, 4, 5, 6, etc. And then we define f, where f of n is the floor of n over 2. Okay, we want to prove or disprove f is 1 to 1, prove or disprove f is onto, and it will go like this. This will be a disprove, and this will be a prove. Okay, so to disprove, we just need to find, and we did one like this yesterday, find 2 elements that map to the same thing. And this is not too terribly difficult with this function, so we can pick many. Notice, let's see, 2 and 3 are both in here. And f of 2, which is the floor of 2 over 2. This is the floor of 1, which is 1. Or I should maybe instead of and, I'll say with. Notice with. Notice 2 and 3 are in z equal to 0 with f of 2. Yeah, that reads okay. And f of 3, this would be the floor of 3 over 2. This is the floor of 1.5. This is also 1. But 2 is not equal to 3. So thus, f is not 1 to 1. Proving a function is not 1 to 1, or even not onto, as we saw. I think we did one like that today. Oh, we did some yesterday. It's an example, right? And so here you find 2 elements in the domain that map to the same specific example. Then you know it is not 1 to 1. Now onto, this is a general proof. So you can't just pick something specific if you're proving something is onto, or if you were proving it was in fact 1 to 1, you would work generally. This is what I will do here. So let's prove this is onto. Well, let me focus on this part, because onto has to do with this. Onto says that the image of the function is all of the codomain. So we start here with, to prove this, we let b be n here. But this is the one that's boxed. Maybe I'll just underline it here. Or I'll put a little bracket. This is the codomain here. I do not mean I'm taking something in the domain and then mapping it or something like this. You start with something in the codomain. Your goal is find something in the domain that maps to B. So you need to show it is in fact in the image. Okay, fine. Well, this is not too bad. So then 2B is certainly here. And by this one I mean domain, but as we will see. So, and f of 2b is the floor 2b over 2, which is the floor of B. But this is just B because B is an integer. So what I have done here is I started with an arbitrary element in my codomain. Then I think about the function, and then I find something in the domain. That's this one. That maps to it. And so I have proved f is on 2, like this, okay? This is in fact an if and only if this statement, as I mentioned in one of the previous examples, but we just need to prove one direction. We suppose R is a relation on A with R equals R inverse and prove R is symmetric. Okay, well, we must think about what it means to be symmetric. So to prove this, you let's say x, y be in the relation. And then symmetric means we need to show that yx is in the relation. And then we will have symmetric. Here we go. Well, as R equals R inverse, what do we know? Well, xy is in R. Maybe I will put that, and xy is in R. Well, in particular, R would be a subset of R inverse, so every element in R would be in R inverse. We have that xy is in R inverse. That's because the two sets are equal, but now I'm going to use the fact that this is actually the inverse relation. So by the definition of inverse relation, we see that yx, is in R. Because by definition, R inverse consists of, well, you take everything in R and you interchange x and y. So well, I should say interchange first and second coordinates. So if you have some element in R inverse, by definition, it must be that if you interchange the first and second coordinates, this is in R. So this would be yx is in R. Oh, gracious. Okay, excuse me. By definition, R inverse, yx is in R. Very nice. So, therefore, R is symmetric. Okay, here's the next one. This is again a problem involving congruence mod n. This is congruence mod 4. If A is even, then A is congruent to minus A mod 4. Okay, wonderful. So let's use the definition. So we assume A is even. And then there exists, let's say, x and z with A equals 2x. Okay, so what this means, okay, A plus A is 2x plus 2x. This is 4x. And so, comma, and 4 divides A plus A as x is an integer. Okay, well that is exactly the statement that A is congruent to minus A mod 4. Like this, okay? This is the last problem in the worksheet. Now I will say this was in our homework, and we did something similar in group work. Which we went over in one of the Zoom videos. We had, let's see, that I think G compose F was 1 to 1, and G compose F was onto, and then we had to prove something about either F or G. This is what we want to prove. We assume F and G are 1 to 1, prove G compose F is 1 to 1. Now, I will underline this because this is the then in the if then. And this is what we're trying to show is 1 to 1. So when we start our proof, we start it the same as every single 1 to 1 proof, where you take two things in the domain, but you really have to think about the function you're trying to prove is one-to-one. And we've done examples of proving different types of functions are one-to-one. This is the one in this example we want to prove to one-to-one. And A is the domain of G compose F. So we take two elements in the domain of G compose F with the function value being equal. And this is whatever function we're trying to prove one-to-one generally, but in this case, this is the function, right? G compose F of X equals G compose F of Y, and then we want to show, in fact, that X equals Y. Okay, and of course, we will use that both F and G are one-to-one. These are our hypotheses. Okay, so we have, I will just rewrite this. We have G of F of X equals G of F of Y. Now, okay, at this moment, I am thinking about the function G, right? Now I have two different inputs and I have G of that, okay? But this came from just rewriting G compose F, but now think about it this way. So we have, this is definitely the case, this is just G compose F of X, G compose F of Y, okay? But as G is one-to-one, okay, it means that, well, these two inputs to G must be the same. So F of X equals F of Y. And then now I use that F is one-to-one. So now I have F. I have two F, or the F of two different inputs being the same. F is a one-to-one function. So as F is one-to-one, well, these two must be the same. X equals Y. And you notice that's exactly what I needed, right? My first sentence says show X equals Y. I have shown X equals Y, and my proof is over. So therefore, we have G compose F is one-to-one. And that's the end of this proof. And that's the end of this extra review. I apologize that my Zoom was not working today, but hopefully this video is helpful.